Welcome to a new lesson. In this lesson, we'll be developing systems of linear equations. Let's just jump into an example. In example 1, we'll be using a diagram to model a situation. So, create a linear system to model this situation. The perimeter of Nunavut flag is 16 feet. Its length is 2 feet longer than its width. So let's take a look at this flag and let's model it. So we know that the flag is a rectangle. This flag has a length and it has a width. We call that the perimeter of a rectangle is 2 lengths plus 2 widths. Because across from the length is another length, and across from the width is there's another width. The question asks, or actually tells us, that the perimeter is exactly 16 feet. So instead of the P for perimeter, we'll put 16. Also, it says in the question that the length is 2 feet longer than the width. This means that if the length was 10 feet, then the width would be 2 less. That means 8 feet. In other words, we can re-establish an equation for the length. Length really is width plus 2. So that whenever you see the length, that could be rewritten as width plus 2. Let's reestablish this perimeter equation, and we'll tell you what this means with the length and the width plus 2. So 16 will give us 2L plus 2W. And this is our first equation, first linear equation. Our second equation is length equals W plus 2. This is our second equation. Now, a system of linear, a system of linear equations, a linear system, is composed of 2 formulas, or 2 linear equations. And these are our 2 linear equations. So now we're going to use these 2 linear equations to see if Dennis has determined that the Nunavut flag is 5 feet long and 3 feet wide. Will this answer, 5 feet long and 5 feet in width, fit into our system of equations? Will these 2 dimensions fit into our systems of equations? And the way we do this is that we sub those values in for our length and for our width. So let's see if we get the right equation. Oh, it's the right answer. So we know that the length is 5, so 2 times 5, plus 2 times width is 3. Will this give us 16? And yes, it does. It does work out. And also, we know that the length is 5. The width is substituted in 3 for the width. And 3 plus 2 is 5. So then this dimensions does work out. 5 feet is the length and 3 feet is the width. Let's take a look at a different example. In this case, we're going to use a table to create a linear system, and we're going to model a situation. Example 2 says, create a linear system to model this situation. In Calgary, a school raised $195 by collecting 3,000 items for recycling. So keyword 3,000, and we know the amount of money raised. The school raised 5 cents for each pop can and 20 cents for each large plastic bottle. So let's use this information to create a system of linear equations. So remember, a linear system, or a system of linear equations, has 2 formulas. And in this case, we have 2 things to consider. We have the pop cans and we have large bottles. And we know when we add them up, we'll get 3,000. So let's call P as pop cans. When we add them to plastic bottles, we'll call it B, we'll get 3,000. And it's good practice to identify what these letters stand for. In this case, we're going to let P represent the number of pop cans. And we're going to let B represent number of plastic bottles. When we add them up, we get 3,000. Now there's also costs associated. We know that if we're going to add them up, what do you mean add them up? You get 195. If we add the cost of the pop bottle of P plus the cost of B, cost of the plastic bottles. But how do we find the cost of these plastic bottles? We know that each bottle is worth 5 cents, or 0.05. And we do not know how many of these pop cans are, or how many of them are. So if we have one pop can, it's going to be 5 cents. If we have 2 pop cans, we have 10 cents. So we're going to multiply this by 0.05 by P. For the plastic bottles, which is described by B, each of the plastic bottles costs 20 cents. 2 will cost 40, 3 will cost 60. We do not know how many of these plastic bottles are, so we're going to multiply B by the cost of 1, which is 20 cents, or 0.20. And here is your second equation. The first equation describes that when we add the number of plastic bottles and pop cans, we get 3,000, and the cost associated with plastic bottles and pop cans is going to be $195. So in part B, the school collected 2,700 pop cans and 300 plastic bottles. We're going to use our linear system to verify that these numbers are correct. This means that if we plug in the values of, in this case, pop cans, which is P, and plastic bottles, which is B, into our equations, they should all work out. So let's plug these values. 2,700 plus 300 will equal to 3,000. So that verifies our first equation. Our second equation now, 195, 0.05 times P, which is 2,700, plus 0.20 times the number of plastic bottles is 300. And let's see if we also add them up to 195. The right-hand side of the equation is 195 as well. This means that 2,700 pop cans and 300 plastic bottles work just fine in our linear systems. Let's take a look at our next example. A store sells wheels for roller skates in packages of 4 and wheels for inline skates in packages of 8. So it's good to underline. So we have packages of 4 for roller skates, and inline skates we have 8 per package. Create a situation about wheels that can be modeled by the linear system below. Explain the meaning of each variable. Write a related problem. So here are two equations for our sister system of equations. And we're going to try to describe what they mean. So, let's start with the second equation. I'm going to label it 1 and 2. The second equation, I believe, tells me that I and R would probably be the inline skates. So number of inline skates. Not really inline skates, but inline skate wheels. And R would be the number of roller skates. Again, wheels. And the second equation tells us that when we add them up, we get 80. So 80 is the total number of wheels. What about the first equation? What about number 1? What does it represent? Well, at least that's my first guess. And just by looking at the first equation, I plus R equals 80, that probably could be the answer. But we have one more equation, that's the first equation, is 8I plus 4R equals 440. Now the problem with this one is that why would we multiply 8 by the number of inline skates? And 8 represent how many per package? So that's very interesting. So there's 8 per package. So here's a little conundrum for us. What does this equation represent? Well, we know that 8 per package, 4 per package, and we have 440. So maybe I is not the number of inline skates wheels. I think, would probably be the number of packages of inline wheels. That's a little bit different. So I is the number of packages in inline wheels, and R would be the number of roller skate packages. Then 440 would be the total number of wheels. So let's restart the problem. This was just sort of a brainstorming, and let's clear all the drawings and we'll restart. So now I represents number of packages of inline skates. R represents number of packages of roller skates. This means that the 440 represents a number or total number of wheels, and while I plus R is equal to 80, when you add up all the packages, 80 represents the total number of packages of inline skates and roller skates put together. So here's a problem that can be derived from this information. A store has 80 packages of wheels for inline skates and roller skates. Inline skates wheels come in a package of 8, and the roller blades wheels come in a package of 4. How many packages of inline skate wheels and how many packages of roller skate wheels are in the store? So that could be one of the possible problems from these equations. As you notice that sometimes your first attempt will not adequately solve the problem, but you will probably have to try a couple different ways to make sure that your understanding is clear and that it fit the system of linear equations that are given to you.